Greetings, Earthlings. Today we're going to take a look at the stupid front panel. We're going to take a look at the actual physical panel itself and the support circuitry for it. You've seen the layout before. There's a bunch of LEDs which show the current state of the program counter, accumulator, memory address, and memory data. There's a row of data switches, and then there's a row of, we'll call them control switches for controlling the operation of the computer. And of course the key lock power switch, which, no vintage computer of the era that this is intending to emulate or recreate should be without. So let's talk about the circuitry. Now for the main computer, I'm using those Euro cards, which are prototyping cards. In this case, for the front panel itself, for mounting the switches and the LEDs, I decided that it was appropriate to make an actual custom printed circuit board to make sure everything's in the right place and not have to, if you have a perforated board that you're working with, for instance, then figuring out exactly which holes things go into can get rather complicated. Now, this is a double-sided board, which contains only the LEDs, the switches, resistors, maybe a capacitor, and the connectors, which will take the signals off to the main circuit boards. So the circuitry that actually drives the LEDs and debounces the switches is in the main computer. The connection between them, I'm using two IDE cables, which are cheap and readily available. I need two because each one is 40 lines, and I need more than 40. So now the drivers I'm using 74 HCT367s, which are non-inverting buffer, hex non-inverting buffers. So these are CMOS chips, and the reason for using those rather than a TTL equivalent is that those can actually source current. So rather than having to pull down the line, which is what you'll quite often see in these things, I can drive it directly, and the cathode of the LEDs are grounded. So these are CMOS chips. I can source current with them. I'm running the LEDs at about 5 milliamps. How did I determine that that was the appropriate amount of current? Well, I connected up an LED with a series resistor in it, a potentiometer, connected it to 5 volts, and adjusted the potentiometer to get the brightness that seemed right. Measured the resistance, and that's the resistance I used. That turns out to be a current drive of about 4.5 to 5 milliamps for the LED. The other thing, of course, is that speed is not a concern. These are a little slower than certainly F-series 74 TTL chips would be, but there's no reason, since it's, a human interface, to worry about a few tens of nanoseconds difference. Now, the control switches have to be debounced, and that is accomplished by an RC low-pass filter going through a Schmitt trigger. And could you do debouncing in the microcode itself? Well, possibly, but this is so simple. The data switches don't need to be debounced. If you think about it, if you're, say, toggling in a program or using it to examine memory, you set the switches, and then you'll press, examine or deposit next or whatever. We're doing this in human time, and so the switches have plenty of time to settle. If you're reading them in a program, when you're running at, the assembly language level, you're probably slow enough that bounce doesn't matter. If it does, if you notice it there, then, hey, you can work around it in software. Not my problem. Maybe that sounds cruel, but I'm sure in reality that's not going to be an issue. Okay, so now we need to talk about fabricating the panel. This requires the use of power tools. In this case, I used a milling machine to drill the holes precisely, and I have a little video on that. All right, let's try this. Going to machine front panel. I've laid it out here. We gotta raise that up so the drill will clear. Let's see. All right, that's 1/2 inch thick. That'll work. Alright, now I've drilled some test holes, and that's what I'm going to use for the switches, which is 3/16, and that is for the LEDs, which is a number 8 drill. Panel layout is like that, so I am actually going to measure. I've got this edge finder, so I will measure to the starting point. Let's see, well, let's do these first, I guess. So I'm 2.4 inches in and 0.8 inches up. That's locked. That's locked. Okay. Oh! 12, and then another 50. I'll verify that. That's why layout marks are so useful. Yeah. Okay. Where's my brush? First row done. Now, I need to move Y direction. One inch. And here's what the finished panel looks like. The LEDs have flat lenses, and so they're flush with the front of the panel. The back side, you see, well, there's the PC board, yep. And there's the IDE connectors for getting the signals on and off. And, of course, the power switch over there on the right, since we're looking at the back of it. So this will need some sort of bezel, some way of mounting it to the case, but I'm not even really concerned about the case yet. I know I can make something work. And I'd rather have this just sitting out on top of the table and have a working computer than having a lovely case and not getting the electronics done. So that's where that stands.